So we'll start straight away since we have the counter there. So maybe let me just make a short motivation in electromagnetism. Actually, we've seen it already in some talks today, but let me go back. So the action is just written here and just an abelian connection. And in electromagnetism, there are two interesting observables you can consider. Since the curvature is gauge invariant by itself, and it's a two-form, you can integrate it directly on the surface, or you can take its Hodge dual and integrate it over the surface. Both these quantities are observable. Physically, this is the magnetic flux, this is the electric flux, and both are well defined. Usually, we prefer to exponentiate them, and and then, of course, if the bundle is non-trivial, then maybe you have some quantization condition for these parameters lambda xi. But I will not go into that. Now, the question is, what can you do in nonabelian Yang-Mills theory? And there the problem is that the gauge transformation, so here just write the infinitesimal version for the connection, implies that the curvature now transforms in the joint representation. It's no longer invariant, which means that just integrating out them, it does not work, not even this way. Okay, so the idea, and actually it will be the goal of the talk, is first of all to take the Hodge dual of the curvature, pair it to some element of the Lie algebra using some invariant pairing. Using Yang-Mills, you have it there, because you start with this compact Lie group, and you just take the Killing form here. But still, the problem is this is not a gauge invariant, because when you do this transformation, like you will act here, but this is fixed. And the idea is to find corrections, so this will be these dots, in such a way that this really becomes an observable. I mean, the similar thing can be done also for the other one, the electric one. This is a bit easier. We'll not discuss it. This has been done, I think, a few years ago by Alexeyev, Mnev, and Chekeres. Okay, so now let me recollect an idea that has appeared before in this, today, I think several times, how to relate Yang-Mills theory to BF theory, and in different ways. Actually, since we are in 4 dimension, I will also consider an extension of BF theory where we also add this quadratic term. So here, A is a connectional form for some also non-abelian Lie group, and B is an add value to form, and this bracket here is some given invariant pairing on the Lie algebra, for example, the Killing form. And this lambda is a fixed parameter, which takes the name of a cosmological constant, because if you look, for example, at Ignacy's talk, there is this formulation of gravity in terms of BF theory, and where you break the symmetry, where this term is really related to the cosmological term in gravity. Okay, now, what we saw in the previous talks is that there is a limit of Yang-Mills theory where you recover BF theory. Here you're doing something else. I'm trying actually to recover Yang-Mills theory from this topological field theory. And the first observation, which is a bit trivial and brutal, but will be the motivation for the rest, is the following. Suppose that you, for some reason, assume that your B form here, B field here, is self-dual for some chosen background metric. And here in this talk, we will work in Euclidean formalism, so this will be a Riemannian metric. So what happens here is that if you select B to be self-dual, this action here turns out to be the Yang-Mills action directly, plus some topological term. I will give this in more details later on. And the idea is then that, okay, what we want to get here is something like, this Hodge dual of the curvature. And so somehow the guess here, since eventually we want to do something like this, is to start with several of this form in BF theory, where we just pair the B field with some Lie algebra element and correct in such a way that this is an observable for BF theory, so that when you make this substitution, here you will get the self-dual part of B, which under taking the Euler Lagrange equation for this action will be the same as putting the self-dual part of the curvature, which is almost the same as considering this observable. Well, plus some other part in the curvature, and then, well, to tell you how to get rid of the other part. Okay, so let me now make this a bit more precise. So let's start from this action, from BF theory, and just restrict to self-dual B form. So the action becomes this one. Then you can do the Gaussian integration over B plus, and you get this action here. And then you just rewrite the self-dual part of the curvature as f plus star f divided by 2, and you get this action here. So this is a topological term, just a Pontryagin class, and this is Yang-Mills theory. So this is slightly different than the first order theory we've seen before, where we put B star B here and integrated out B. Here, where there is no star here, it's not necessary because B is self-dual. So the other difference is that the additional field I've introduced here to describe this version of first order Yang-Mills theory is not an arbitrary two-form B, but a self-dual one. But still, this also provides a way of constructing a first-order version of Yang-Mills theory. Now, this will give you Yang-Mills theory plus the specific choice of the topological term. Notice that the coupling constant here is the same as for Yang-Mills theory, but actually you can change that. The point that you can deform the original BF theory by adding the topological term. This is a deformation that doesn't break the symmetry. And so if you repeat this computation here, at the end you get Yang-Mills theory plus this topological term. And so here you can get whatever you want. Okay. And the other observation is that if you restrict the BF theory observable, which I will construct later on, you get this observable for this first order Yang-Mills theory with B plus here, and then this B plus will be essentially the same as putting the self-dual part of the curvature here. Okay. Now, now there are two things that we wanted to do here, right? First, restrict to self-dual curvature. Second, self-dual B field. Second, construct this observable for BF theory. So point 2 is achieved in terms of coupling the BF theory to a two-dimensional field theory, actually another BF theory, defined on the two-dimensional surface. And the full construction will require the BV push forward. So one version of this construction has already been mentioned in a couple of talks today. This is the case where lambda is equal to 0, and today we'll extend it to the case where lambda is also different from 0. And then the other part here, like recovering Yang-Mills theory from BF theory and using this idea to construct an electric observable for Yang-Mills theory, can be put into better terms, not just as a brutal substitution of B self-dual into the action, which is just said, okay, just observe that inside your theory, topological theory, here, but actually doing something better, actually showing that Yang-Mills theory plus some corrections can be obtained as an effective theory from BF theory. Okay, so now let me go a bit more into details. So let me first start with the abelian BF theory, just as a warm-up. So in 4-dimensional again, so now A is a 1 form, B is a 2 form, and so in addition to this 4 form, I can also add this other 4 form. The equation of motion simply says that B is closed and that the curvature is lambda B. So for lambda equal to 0, which is the case we discussed long ago and was discussed today, these two equations are independent, whereas if lambda is different from 0, this equation is just a consequence of the second one. Now, there are infinitesimal symmetries. So there is a symmetry generated by gamma, which is just the infinitesimal gauge transformation. But then there is another symmetry. So for lambda equal to 0, you see that, you can shift B by an exact 1 form, and then integrating by part, this term disappears. If lambda is different from 0, this transformation changes this term, but you can compensate it by shifting the connection. Okay, so these are the symmetries of abelian BF theory. And now what you realize is that, the integral of B is an observable. Right? There are no gauge transformation on B. B transformed by an exact term. So if you integrate B over closed two surface, this is an observable. Yes? Are? Which one? Variables?
At the bottom line, you have little k and little l.
No. It could be at the moment they can be whatever. Then, of course, depending like what really your Yuan bundle is, you might have to restrict them. Okay.
If they can be continuous, why not just take the exponent? Why do you want to exponentiate?
No, yeah, because the better version is when you exponentiate and they will not be continuous. It will be like, yeah. But just if you consider infinitesimal symmetries this way, of course, this works, no problem. What does not work if lambda is different from 0 is the Wilson line. The Wilson line is an observable, or integral of A along a loop is an observable for lambda equal to 0, but not for lambda different from 0 because you have this shift. So in this case, you will lose this observable, or I mean, you should try to recover it by deforming it. Now, in the nonabelian version, we have some principal bundle. I will focus just on the Lie algebra of the Lie group, and the action is written here. So as I said, A is a connection, B is a two-form in the joint bundle. Well, if you are in 4 dimensions, this is just a two-form, and I can also add this other term. These are, again, the equation of motions. Again, if lambda is different from 0, this equation is a consequence of the Bianchi identity. And now here I have the full infinitesimal non-abelian symmetries. So again, gamma generates the gauge transformation, as usual. And then we can now change B by the covariant derivative of some one form. By the Bianchi identity, this disappears. And if lambda is different from 0, this generates some terms here that have to be compensated by a shift in the connection. OK, and now the idea is now to try to deform this observable we had in the abelian case into something where I have to correct. So first of all, since B now is, well, let me, for simplicity, suppose that the principal bundle is trivial. So B is a Lie algebra value to form. So I have to couple it to some element of the Lie algebra to get a number. Then I can exponentiate, integrate, but I will have to put corrections. And so I will describe how to produce these corrections. And then at the later stage, you want also to consider global, not only infinitesimal symmetries. And so it will turn out that, well, this psi should also be quantized in the appropriate sense. So it will not be just a generic element of the algebra. It should belong to some cojoint orbit, which is quantizable. OK. Now, what I said before is that you can see Yang-Mills theory inside the spatial field of BF theory. So you have the BF fields, A and B, with its action. You have a submanifold here, where you set the anti-self-dual part of the B field to 0. And if you restrict the action here, you get the first-order Yang-Mills action. Now, you can also go to the BV formalism, which I will explain later on. It's some generalization of BRST formalism, where you introduce also the ghosts and other variables so that you can make sense of gauge fixing and integration, avoiding the problem of the degeneracies of the action. And it turns out that this part works essentially the same way. The BV fields for Yang-Mills theory are a submanifold of the BV fields for BF theory. And if you restrict the BV action for BF theory, you get the BV action of Yang-Mills theory. But this is still a rather stupid observation. The interesting observation is that actually you can compute the integral on the transverse direction by some appropriate gauge fixing. So we'll do this thing here. So you start with the BV action for BF theory, choose some gauge fixing for the transversal direction, integrate out, and what you get is Yang-Mills theory plus some corrections at order h bar, which means that classically it's the same Yang-Mills theory. It's the form only at the quantum level. So it's somehow, you might think that like what you want to do here is to quantize Yang-Mills theory either by deforming the action at order h bar or by changing. You can also think that this correction here as choosing a different functional measure. Or actually, another version that we'll see later on, you can see is this correction as something you can somehow transport from the theory to the observables. And so if you have an observable for this deformed Yang-Mills theory, basically you can shift this part into the observable itself and make it into an observable for Yang-Mills theory as the usual way. In addition, there could be some zero modes in the transversal direction. So here I really think of like the moduli space of zero modes, critical points in the transversal directions. In this talk, I will completely ignore them. One way is to focus on examples where they are not really there. And the simplest situation is just you work over R4. Your 4 manifold is R4. You vanishing condition at infinity, then these 0 modes are not there. Other situation, for example, the closed manifold, if you work around a flat connection whose cohomology vanishes, also they're not there. In general, they will be there. And the point of you cannot integrate them out as they are, but you can actually introduce some observables depending on the well, essentially, yeah, on the transversal field, which somehow soak the 0 modes, and they will basically play no role at the end. Okay, so the other remark was that we assume that I can produce also an observable for BF theory this way. And then, essentially, when I integrate out the transversal direction, I will produce an observable for this theory. And, well, this observable will start just by substituting B plus for B. Just you don't see the anti-self-dual part. And then, of course, when you go to the second order theory, this will be just the self-dual part of the curvature, and then you can split this into F plus F star. So this is the term we want to have, and this is the term we want to get rid of. And there are several ways of getting rid of it. I will not discuss them here, but quickly. I mean, one way is actually to reformulate, somehow deform this observable in such a way that this term disappears. Another way will be to multiply this observable by essentially these observables with the minus sign, so that the two things will compensate. And the second construction actually requires a framing for the surface, because otherwise this would not be an observable. Okay, but these are possibilities. Okay, now let me go to the meat. How do we construct this observable for BF theory? And the idea is to start from something which is gauge invariant and defined on the surface, and which has some leading term, which is integral of B. So the idea is to construct this observable itself as some sort of functional integral of a theory that lives on sigma, but is coupled to the ambient field. So this theory will also be a BF theory. So here, I mean, the BF field for this two-dimensional theory denoted here as alpha and beta. So alpha is a 1 form, and beta is a 0 form. We are in 2 dimensions, so you want to have this kinetic term, beta derivative of alpha. This should be a 2 form, so beta is a 0 form. And they are coupled to the ambient theory in the sense that what we can do, we pull back the principal boundary of the manifold to the surface sigma, and we regard alpha and beta as 1 form and 0 forms taking values in the adjoint bundle for the pullback. Okay, so this means that here I have to put the covariant derivative with respect to the pullback of the ambient connection. There is a term that I can put here, just pairing B with the bracket of alpha with itself. So alpha is an adjoint bundle, so I can take the Lie bracket. And this is actually the term I must put if lambda is different from 0. And finally, there is an important term, which is just a pairing of beta with the pullback of the ambient B field. So this beta is a 0 form, B is a 2 form, so I can pair them and I get a 2 form over sigma. Okay, just to mention, the observable that was mentioned a couple of times today and goes back to my work with Rossi corresponds to the case where this term is not there, where lambda is equal to 0. Now, the first observation is, why is this a gauge invariant? So let me recall for you the infinitesimal transformation for the ambient BF theory. So we have the gauge transformation with parameter gamma and the shift symmetry with parameter theta. And of course, this functional is not invariant under this transformation, right? You have A here and B here. It transforms somehow. But actually, what happens is that this transformation can be compensated by this change of variables. So here I write things only in the infinitesimal level, but of course you can exponentiate. So the idea is that you can compensate this transformation A and B by this transformation on alpha and beta. So these are the symmetries, infinitesimal symmetry of the ambient theory, and these are infinitesimal changes of variables. Okay, so the idea is that formally, this expression now, this whole integral is invariant under the symmetries of BF theory. So we compensate the symmetries by a change of variable. Okay, so this is somehow the idea. Now, the problem is, okay, how do you make sense of this functional integral. So as usual, you want to make sense of it again, perturbatively in terms of Feynman diagrams. You have to check that the critical points are non-degenerate and so on. So first of all, let me discuss the critical point and then the infinitesimal symmetry for the two-dimensional BF theory. So the critical point are these equations. So again, essentially, these are the analog of f equal to 0 and the b equal to 0. Now there are some sources coming from the ambient theory. And for simplicity, let me suppose that I start I want to work in the ambient theory around the trivial solution. So I suppose I have a trivial connection, which I just denote by 0, and the trivial two-form B. These are a critical point for the ambient theory in case of a trivial bundle. So for this choice, the equation becomes these ones. And you can see that there is an interesting solution where I can set alpha, the one form alpha, to be exactly equal to 0, and the zero form beta to be constant. For a reason that at this moment is useful to actually to rescale this constant by h bar. Okay, so you see that this satisfies this equation. So the advantage of this solution is that, well, when I evaluate my action functional for the two-dimensional BF theory on this solution, I get one term, which is h bar psi paired with b. Okay, for I think, yeah. Okay, here I didn't write the pairing. Okay, but the pairing will be here. So the observable will start with this term, and then there will be some dots that come from the Feynman diagrams. So this is exactly what we want to get. And the reason that, well, I don't want to get the 1 over h bar factor here, which was part of of this definition. So I choose the critical point to start with h bar, just to make things consistent with the general notation. Okay, so this is fine. What is the problem? Well, the problem that we want to make sure that we can start with the perturbative expansion, and the problem that, okay, there may be symmetries, and so which means that the critical points are degenerate, and we have to do some gauge fixing. So, okay, what are the symmetries? Well, since it is a BF theory, you might guess you should have some sort of BF theory symmetry as well. So, well, what are the usual BF theory symmetry? Again, you shift the one form by the covariant derivative of something, and just let this zero form act in the joint representation on the B field, which is here is beta. So these are the symmetry you can write down. And actually, well, to make sense of the whole thing, you have to also to shift by lambda. Somehow here you have to think of these terms, dA alpha, alpha bracket alpha, as part of some generalized curvature. Actually, if you put together, maybe let me write it down, it's natural to think of f of A plus alpha as f of A plus dA alpha plus 1/2 alpha bracket alpha. So this is the term that you have in the ambient theory, and these are actually the two terms you have here. Okay, and so this suggests that, you should have a gauge transformation that, well, takes the covariant derivative of A plus alpha, and this is precisely what you get here. Okay, so this is the covariant derivative of rho with respect to the connection A plus, actually, lambda alpha, probably. Okay, should probably write some lambda here. Okay. Okay, so, okay, let's try to apply this, these supposed symmetries to this action functional, and the result is this expression here. And this expression here actually is proportional to this Euler-Lagrange equation. So in particular, it tells you that you are on shell for the ambient theory. This is really a symmetry. As soon as you go off shell, it's no longer a symmetry, but if you're on shell, that's where the computation dominates. This is a symmetry. So basically, you have to do some gauge fixing for this symmetry. What makes things a bit non-trivial, not just a bit, is that, as I said, as soon as you go off shell for the ambient theory, this is no longer a symmetry, but you're still gauge fixing it. So you might expect that something is a bit weird, and actually the solution for all of this is to use the BV formalism. The BV formalism actually takes care of all this problem, and everything is fine. Okay, I will describe the BV formalism in the second part. Now, let me quickly tell you what happens if you now start computing Feynman diagram for these observables. Well, you have to do it consistently now using the BV formalism, taking gauge fixing, and so on. So there will be a propagator between alpha and beta, which, say again, I work around the zero background connection. So here there will be some kinetic term, which is just beta d alpha. So you'll need some propagator, which essentially invert this d here. And this is a typical thing also you do in perturbative Simon theory or in Kontsevich formula and so on. So this is just, I mean, write down the integral kernel for this propagator. This is just a one form on the surface sigma, which satisfies certain property. I mean, a form of configuration space of 2 points of the surface sigma with certain properties. And you can use it to construct Feynman diagrams. Well, if you look at the vertices appearing here, it's not difficult to see that basically these are the kind of Feynman diagrams you can produce. So for lambda equal to 0, you can produce only two kind of diagrams. First, you can produce these long snakes. So you start with psi bracket A, and using the propagator, you connect it to some other ambient field A, and so on and so on, and at the end, you connect it to some ambient field B. And the other thing you can do is to produce a wheel, just closing everything. And I mean, at each vertex, there is an ambient field A. And if lambda is different from 0, you have these additional kind of diagrams that you can construct. Okay. So what you can do here is that actually you now can take this expression here, and if you didn't believe me that, doing this functional integral produces an observable by this observation, you can actually check that this expansion in Feynman diagram is an observable for BF theory directly. And the reason is that, for example, I mean, you can have some gauge transformation on A, which is a covariant derivative of something. And what you can do, you can integrate by parts. And when you integrate by parts, actually it turns out that, under some assumption, this propagator actually is a closed form. So you just use Stokes' theorem, and using Stokes' theorem essentially let two subsequent points in each of these diagrams collapse together, and then you will have terms where, for example, you have two A coming together. This is the A commutator A part of the curvature. You will have also D move to other A's, so that will be the dA part. So we'll have parts with the insertion of the curvatures. You will have terms where the B is also moved. You have terms where, okay, and so on. And you have like your Gauss field here, for example, but is also moved to some A or some B or from here. And so this produces the other part of the gauge transformation. So you can really check directly that these diagrams are gauge invariant. Okay. The other observation is that since we are in a topological theory, this observable is also constructed in a topological way. Didn't make any choice that broke the invariance under the diffeomorphism. You should expect this expectation value in field theory to be a topological invariant. So actually, this depends not only on the ambient manifold M, but also on the embedding of the two surface sigma. And so you should expect that this is a two-knot invariant. So an invariant of the embedding up to isotopies. Actually, we checked this long ago in the case lambda equal to 0, and in a particular situation where M is R4 and sigma is an embedding of R2, that this is really a topological invariant. And then some people checked that basically, all the order and perturbation theory you get here are related to the Alexander invariant for the two-knot. What is new here now are the diagrams for lambda different from 0. See here, there are more terms here, which produce new potential topological invariant, which potentially may not be just coefficients of the Alexander invariant. So this could be some new topological invariant for the two-knot. Okay, the other observation, which is relevant for today, is that upon integrating out these BV fields in BF theory that are transversal to the BV field for Yang-Mills theory, you could produce an observable for Yang-Mills theory, which will be the nonabelian version for the electric observable. Okay, so now let me go into some details of the BV formalism. So let me start with this very formal version, which of course I can formulate more abstractly. And the part where I'm cheating here, that this makes sense for finite dimensional BV theory. And then, okay, you have to understand how to extend it to field theory. So the idea is that you start just having an odd symplectic manifold. So F is a supermanifold, 2 is a closed non-degenerate 2-form, odd with respect to the internal degree. And there is a very interesting observation that actually came long after Batalin and Wilkowicki, such as originally due to Hadverdian, that such a manifold possesses a canonical operator, denoted by delta, that acts on half densities. So, what are half densities? So, first, what are densities? So, whenever you have a supermanifold, there is a natural line bundle that you can associate to it, which basically the transition function are just the Berezinian of the transition function of the manifold. Here, assume everything to be oriented. So you can also take the square root. So half density is a section of the square root of this line bundle. Half densities are quite interesting. Well, on the one hand, you can say, wait, if you square them, you can integrate them over the manifold, or you can pair them one with the other. So half densities are nice because they're somehow the candidate for building some Hilbert space. But they're also interesting because we are talking about a symplectic manifold. So the natural object to consider a symplectic manifold are Lagrangian submanifold. Lagrangian submanifold are, okay, in this finite dimensional setting, in some sense, half-dimensional. And it turns out that actually, if you restrict the half density to a Lagrangian submanifold, you get a density over the Lagrangian submanifold. So half densities are actually the thing you can integrate over Lagrangian submanifold. So that's why these are very natural objects to consider on a not symplectic manifold. But the interesting observation that there is this canonical operator acting on them, which scales to 0. So it's a coboundary operator. And in addition, this coboundary operator has the following properties. So these essentially were proved by Batalin and Wilkowicki in the local setting, where essentially you don't distinguish much between half densities and functions. But okay, now these are global statements. And so the observation is the following. So first of all, if you integrate a delta exact half density on a Lagrangian submanifold, you get 0, assuming the integral is well defined. And the second observation is that if you have a delta closed half density and you have a family of Lagrangian submanifold depending smoothly on some parameter t, the integral of the half density on the Lagrangian submanifold t does not depend on t. So the integration is invariant under the formation of Lagrangian submanifolds. And this is somehow, the key for the application to field theory. The idea is that you want to make some gauge fixing in field theory to make sense of your integral, but you want to make sure that this choice is irrelevant, so you want to make sure that whatever you compute is invariant under the formation of the gauge fixing. And basically, this is the theorem you use to prove that. Of course, theorem in the finite dimensional case, and theorem upon regularization in the infinite dimensional case. Now, I will not prove this, but just to give you a feeling why one might expect this, let me just cheat a bit and simplify things. So this goes through observation by Witten and Schwarz. The first observation is that every odd symplectic manifold actually admits global Darboux coordinates. So it can always be written as a cotangent bundle. This pi means that the fibers has odd coordinates and the base is coordinates. And so this is non-canonical. It's a non-canonical symplectomorphism, but it's always possible to do that. But once you are here, there is a canonical identification between the half densities of this odd symplectic manifold and the differential forms on the base. Now, on the differential forms, you have a canonical operator that squares to 0, which is the exterior derivative. And so you can use this isomorphism to map it to some operator here. And this is actually how you get this canonical delta operator acting on half density of an odd symplectic manifold. Okay, so this does not yet prove this part here. You have to check what happens like when you use this symplectomorphism, but this has been done by Hadverdian, and there are also more modern way of seeing this. The second observation is that here on this side you have Stokes' theorem, right, which looks somehow similar to this, right? The integral of an exact form on a closed cycle is 0, and if you have like you deform a closed cycle, the integral of a closed form doesn't change. And actually, there is a relation to the left-hand side, namely that, well, basically, to each submanifold of the base n, you can associate its odd conormal bundle, which would be Lagrangian here. And so you can understand integration of a differential form on a submanifold of n as the integration of a half density here restricted to some Lagrangian submanifold. And so in this case, in this restricted case, these two statements are just Stokes' theorem. Okay? What is a bit more general here is that there are Lagrangian submanifolds that are not odd conormal bundle. They are deformations of odd conormal bundle, and this is actually, well, the result of Batalin-Vilkovisky that actually also under these deformations, well, you still have this property, also for these other Lagrangian submanifolds. Okay. Now, let me just generalize the previous construction to the case where your odd symplectic manifold is presented as a product of odd symplectic manifolds. And so it turns out automatically that the canonical delta operator also splits into the two canonical delta operator on the two factors. And what you can do now is that you can choose a Lagrangian submanifold of the second factor only and integrate only on that factor. So what you do is now you take a half density on the product, you restrict it on this Lagrangian submanifold, right? So what you get is now essentially a density over the second factor parameterized by the first factor. So if you integrate, you get, of course, you get a half density on the first factor. Okay? So this partial integration tells you how to go from half density on the product to half density on the first factor. And essentially, a slight modification of the observation above, like theorem of Batalin-Vilkovisky and other people, is that actually this integration commutes with the delta operator. So if it's a chain map with respect to, so here is the whole delta for the product, and here is delta on the first factor. So these are the crucial observation. And the result is the following. Suppose that you start with some delta closed half density on the product, define its effective version as the integral over this Lagrangian submanifold. Now the fact that this is a chain map tells you that this effective half density is still delta closed. So if you think of the object you are interested in as the closed half density, this construction produces for you effective half density that still are good for you. The second observation is that you might want to deform the Lagrangian submanifold, and now it turns out that, well, this is not zero, but you can show that is a delta 1 exact. So now the idea is that you should think of the correct object in your BV theory to be delta closed half density modulo delta exact ones, and this partial integration, which we call the BV push forward, is compatible with this. It's now well defined in this well, delta cohomology. Okay, just a comment. This construction can be generalized also to non-trivial bundle, but you have to put certain condition with kind of bundle, like from the non-trivial bundle for this to make sense. Okay, now typically, especially in field theory, you don't really talk about the half density, right? You talk about the action functional. So somehow we want now to translate this in terms of functions. So the idea usually is the following. So fix some reference, nowhere vanishing and delta closed half density rho. And then once you've done this, you can define an operator, let me denote it momentarily by delta sub rho, acting on function. So the idea is that whenever you have a function alpha, f, you can multiply it with the half density rho. You get some half density f rho. You can apply the canonical delta. You get half density again. But since your rho was assumed to be nowhere vanishing, you can recover a function by dividing by rho. So this is how you define the new delta acting on functions. And this is actually the BV operator considered by Batalin-Vilkovisky originally. And it turns out to have these two interesting properties. Actually, well, this property, the other one is more or less a consequence. So it turns out to be a second order differential operator. Namely, delta rho applied to a product of f and g is not just delta f times g and f times delta g. There is some correction term. And the correction term can be computed and turns out to be the Poisson bracket with respect to the symplectic structure. So here I'm using well, the notation by Battaglia and Vikovitsky with round bracket instead of curly bracket. They used it to stress that it's an odd Poisson bracket and not an even Poisson bracket. What is notable in this equation is that delta on function is defined using a reference Hooft density, but the correction term is completely independent. It's always the same as the Poisson bracket. Now, if you extend this to exponential, so suppose you have some even function f, and you apply delta, so this should be this delta rho, to an exponential, what you get is essentially, since the second order operator, is the exponential times this expression here, which is just delta f plus 1/2 the Poisson bracket of f itself, which is not trivially 0 because f is even and the bracket is odd. Okay, now in physical application, what you do is, okay, you move to the infinite dimensional setting. First of all, you formally assume that it makes sense to consider some sort of reference Lebesgue-Berezinian. And then you are interested in functions of the form exponential of the action functional, usually with this prefactor I over h bar. So, well, formally believing in this equation, the infinite dimensional case tells you that the equation that delta rho is equal to 0 is equivalent to this equation here, which is I wrote here. Okay, so here is k by h bar, and this is called the quantum master equation. And now, okay, what are the problems? Well, the problem is that this reference Lebesgue measure, of course, doesn't make sense. This canonical delta operator does also not make sense in the infinite dimensional setting, so you have to regularize theory to make sense of it. On the other hand, this equation is a bit nicer in the sense that, well, this term doesn't make sense before regularization, but in the classical limit h bar equal to 0, you just retain this term here, which makes sense, because this is just a Poisson bracket on an infinite dimensional manifold. It makes sense for an appropriate class of functionals. So in typical setting, the symplectic form is local, and so this bracket makes sense for local functionals. Okay, so but assuming you have a way of regularizing the theory and then, well, also renormalizing if needed, then you can make sense of this equation. You can make sense of the integration over a Lagrangian submanifold of an infinite dimensional space of fields. And in particular, you can do this BV pushforward. So I assume now that I have some field theory with a space of field F, which I can write as a product of space of fields F1 and F2. I have an action functional on F that satisfies the quantum master equation. And then I can compute this integral where L is a Lagrangian submanifold of the factor F2. So this will be some Hooft density. So assuming that I have also a reference Hooft density ρ1 on the first factor, which assumed to be non-degenerate, then I can rewrite this integral as ρ1 times a function. And again, since this was an exponential function, essentially you can rewrite this as an exponential function as well. And so this is what is called the effective action. Now, the naming comes because of a very simple, well, not so simple, not simple, but an obvious application of this is splitting the original space of fields into infrared and ultraviolet components. So suppose you work, say, on Rn, and you just take Fourier expansions, and in BV theory, and the idea that you can integrate out the ultraviolet fields to get an effective theory on the infrared fields. So this is essentially Wilson idea, but now promoted to the BV setting. And somehow the theory of BV setting, well, extended to the infinite dimensional case, tells you that if you start from a solution of a quantum master equation, the effective action will also be a solution of the quantum master equation. So up to regularization and renormalization, everything is consistent. Okay, so now the main statement I want to make is the following. It's the following claim. Start from the BV theory for BF theory with a cosmological term in 4 dimensions. Split the space of fields into this product, where F1 are the BV fields for Yang-Mills theory, and F2 is the rest. Notice that, well, in this case, F is an affine space, so this actually can choose this complement, F2. And then, upon choosing an appropriate Lagrangian submanifold of F2, you can compute the effective action and show that it is the BV action for Yang-Mills theory, the standard one, plus one correction at order h bar and nothing more. So this correction turns out to contain, well, for in the nonabelian case, to contain some non-local terms, but it's at order h bar. And actually, there is a nice gauge fixing which has no higher order. So the whole correction is concentrated at order h bar. In particular, in terms of Feynman diagrams, this correction term is constructed entirely in terms of one loop diagram, which means that also the normalization is much, basically almost not needed. So yeah, let me mention what happens in this integration. So the first observation, okay, first here you might be puzzled in the sense that BF theory is a topological theory, which means that it's invariant under diffeomorphism and there's no local degrees of freedom, whereas Yang-Mills theory is a physical theory depending on the metric, not invariant under diffeomorphism and with local degrees of freedom. Actually, the two polarizations of like the photons. Now, what happens is that when you do this integration, so first of all, you have to introduce a metric. Actually, a metric is already introduced in this splitting, but also introduced in the gauge fixing here. And so the result is not unexpected that the effective theory will no longer be diffeomorphism invariant. The second observation, which is a bit less trivial, is that actually this integration over L integrates out more ghost fields than fields of ghost number 0. Yeah?
In this effective theory,
Yes.
is the beta function negative?
Well, this part here is the same Yang-Mills theory.
So
It's the same. It's exactly the same.
so it's a deformation of the ordinary Yang-Mills?
So there is this additional term here. Yes. Yes.
How does it change the Lubbock spectrum? Is it still confined?
Well, that I don't know. I didn't check. But actually, the one thing you can do is instead of considering this theory, you can still consider the standard Yang-Mills theory and somehow, well, basically the construction I will provide will give you first an observable for this effective theory, but then you can somehow move this correction term to the observable. So then you will keep working with the standard Yang-Mills theory. This will be just some term that you have to add to the observable. So you just focus on the standard Yang-Mills theory, whatever you know Yang-Mills theory about renormalization, beta function, and so on. So it's not, you don't have to consider this effective theory. You can really focus on the standard one.
But then how is it different from the ordinary Yang-Mills?
Well, there are some additional non-local terms here.
But what are the observables? Maybe the Lubbock spectrum?
The observable, well, what I'm going to construct is an electric observable, so an observable that corrects just the integration of the Hodge dual of the curvature on the surface by some additional local terms that make it gauge invariant. So the idea is similar, like suppose that you know the Wilson line in Wilson loop in the abelian case, which is just exponential of the integral of A, and then you see that in the non-abelian case is not invariant, so you have to start adding corrections. And suppose you didn't know from the beginning that this is just the holonomy, so a path order exponential, you just by hand try to compute the corrections. So you can write this as integral of A of a loop, as in the abelian case, which is not gauge invariant, plus corrections. So you have to add these non-local corrections to make an observable. This is exactly the same thing. Okay, so let me tell you the other observation here is that in this partial integration here, we are integrating out more gauss fields than fields. So here I mean fields of gauss number 1 or 2, actually in this kind of theory, then field of gauss number 0. And the result is that the effective theory now has local degrees of freedom. Point that, well, the local degrees of freedom are computed actually in the derived setting. You really have to go to the BV cohomology. So it's not essentially the degree 0 part, Gauss number 0 part of the cohomology. And so basically, it's not only the fields, but it's the fields modulo their own gauge transformation. So the idea is that like the effective theory here will have less fields than the original theory. We are integrating out some of the fields, but we are integrating out even more possible gauge transformation. So we're breaking the symmetry more than the number of fields we get rid of. So as a result, the effective theory will have local degrees of freedom. Actually, the correct number. And the final observation is that actually these correction terms are only one loop diagrams. exponential of one loop diagrams. So these actually might also answer your question. I mean, these one loop diagrams might not be too dangerous for like all the other considerations. And actually, yeah, essentially you might think of them really as part of the determinant that for this fiber integration, so somehow the remnant of the change of the functional measure. Okay, so now let me tell you what to do for the observable. So remember, we had this classical observable on the surface with the fields were denoted by alpha and beta. Beta is a 0 form, and alpha is a 1 form, taking value in the Lie algebra. So what you can do, you can promote this to a BV action in such a way that the sum of the BV action for BF theory and this BV action satisfy the quantum master equation. Okay? So this BV action satisfies the quantum master equation by itself, but you want also the sum to satisfy the quantum master equation, which means that now you can consider this as a new action on the total space of fields. And when you integrate out the now you now choose a Lagrangian submanifold on the space of fields for the surface observables, you get some effective action, which you can actually rewrite this way, because there is some factor here, or actually here, so some summand in this action here. So you consider this as a total action, which satisfies the quantum master equation, but this term does not depend on the surface field, so you can take it out from the integral. Okay? And then the integral will produce some functionals of the fields, of the BV fields for BF theory, so I can rephrase everything this way. And now, again, the theorem of the BV pushforward says that since this was a solution of the quantum master equation, well, the delta applied to this expression is 0. Since we know that the BV action for BF theory is a solution of the quantum master equation, this tells you that this functional here is a quantum BV observable for BF theory, automatically. Okay, so this is what you want to do. Now, the last step is to go down to Yang-Mills theory. So what you can do is, well, you take this expression here, which is delta closed, you integrate it over this other Lagrangian submanifold, this Lagrangian submanifold for the fields that are transversal to the Yang-Mills fields in BF theory, and now then you can, well, rewrite this as some expression. I want to somehow factorize the effective action for this theory. Well, I can do it. I mean, I can compute this integration and multiply by, well, the inverse of this exponential. I can also do that. So I can get this thing, which I call the effective observable. Now, the point is that since this was delta closed, this whole expression, this whole product is delta closed, which means that this observable here is, I mean, this functional here is an observable for the effective action I got here. Okay? But actually, I might decide to consider this product here, which I call O sigma Yang-Mills, and since the action for Yang-Mills theory satisfies the quantum master equation by itself, this observable will be an observable for Yang-Mills theory by itself. So now notice that I don't want to put this correction term into the action functional. I put it inside the observable. So now my surface observable for Yang-Mills theory consider of some Feynman diagrams coming from this observable for BF theory, but also out of this other one-loop diagram here. So everything is inside here. So now this observable is really highly non-local, but it has a leading term, which is the integral of the self-dual part of the B field on the surface. So this is it. Now let me do some final remarks that, I mean, this BV pushforward is compatible with the expectation value. So the result is that the expectation value of this Yang-Mills observable in Yang-Mills theory is the same as the expectation value of the BF observable in BF theory. So this is an invariant for the 2-0. So this is really a topological invariant for topological observable for Yang-Mills theory. So it's some sort of topological defect. And well, now one thing one could try to see is to study, for example, what happens if you try to go through these topological defects by some other fields, and to study, I mean, to view it also as a generator of some higher symmetries. The second observation is that it's highly non-local. Well, it's not only supported on sigma itself. I mean, you really have a cloud, not only here, but also inside here, there are clouds observable. And the result of this is that the product of this surface observable with the Wilson loop is not an observable. Notice that in the abelian case, the product of a surface observable and the Wilson loop is an observable if well, the intersection of the two cycles is empty. In the general case, since this is highly non-local, this is not. Notice that, well, in BV, well, observables are defined in terms of this quantum master equation, so in terms of this delta operator, which is a second-order operator. So the result is that observables do not form an algebra. So the product of two observables is not necessarily an observable because, I mean, somehow the cohomology operator you use is a second-order differential operator. Okay, so this may happen, and actually it happens here because I mean the non-local term of these observables contain the momentum for the connection A, which is appear in the Wilson loop. So even if gamma does not intersect sigma, there will be some terms here that see the connection here. So this product is not an observable, which means that you cannot measure them at the same time. I think that in the abelian case, it was observed that like if you take somehow non-trivial bundle, really, also there you cannot somehow observe or measure the Wilson loop and the surface observable at the same time. So this somehow in the non-abelian case is even worse. Okay, so I think I'm done here.